So this lesson here is looking at two really important differentiation rules, the product rule and the quotient rule. And so first of all, it just should be stated that if you have two functions that are being multiplied to each other and you want to find the derivative of them, it is incorrect to just find the derivative of the first times the derivative of the second. And some of our group problems will kind of prove that's wrong. But that's incorrect. What is correct always is this. If you want to find the derivative of any two functions being multiplied to each other, you find the derivative of whatever's first times the other function as is plus the other way around. So just the first equation as is and the derivative of the second. It's really not that complex. And keep in mind, the order of this doesn't really matter. Essentially, if you have any two functions being multiplied to each other and you want to find the derivative of that, or if you want to think of a function as being a product of two separate functions being multiplied to each other, find the derivative of one times the other plus the other way around. The quotient rule, a bit more complex but similar. If you want to find the derivative of one function divided by another, it's a derivative, and this time the order matters. Just like when you're dividing, it matters what's in the numerator and in the denominator. So it's a derivative of the numerator times the denominator as is minus the other way around. The numerator as is times the derivative of the denominator. And all of that is divided by the denominator squared. Not the derivative of the denominator squared. And so, of course, we just need to use some of these. And so here I have a function that I can visualize as, an exponential function times a cubic function. And there's other things I could do. I could distribute this out. And there's nothing wrong with doing that, but I don't think that's going to be helpful. In fact, if I did that, I'd still have to use this rule. And so I'm just going to think of it as an exponential function times a cubic function, or a polynomial function. And that said, the derivative of this then would be found by finding the derivative of e to the power of x, which is e to the power of x, times fx cubed minus 2 left alone, plus the other way around. So e to the power of x left alone, which is the same thing. Hence, e to the power of x is such a nice function to work with, times the derivative of the cubic function, which is 15x squared. And I'm done. Now I can clean this up in various ways. For example, if I look at this, one fairly easy thing to do is take out a factor of e to the power of x from both of these, and then I have 5x cubed plus 15x squared minus 2. If I just kind of put that together, that's it. They're both good. So again, I didn't really have to do that last step, but I hope that last step makes sense because that is a slightly more simple function to deal with. All right, so let's look at this. I have x squared plus a over x cubed plus b. Again, a and b are just some constants. So I want to use the quotient law here, or the quotient rule, I should say. So first, now the order matters. The derivative of the numerator. The derivative of the numerator is 2x plus 0, because a is a constant. So just 2x times the denominator left as is. So x cubed plus b minus the other way around. The numerator as is times the derivative of the denominator, which is 3x squared plus 0, or just 3x squared. Right, and all of this is divided by the denominator, x cubed plus b, all squared. Now that's it. I am done, but I can probably clean this up a bit. Distribute, the 2x and the 3x squared. All right, and then, this is not inherently any better than what I had before, but I do see some like terms here. Again, 2x to the power of 4 minus 3x to the power of 4. So I might as well put those together and get negative x to the power of 4. But again, in terms of just finding the derivative, I was done 2 steps ago. All right, let's look at this one. Ooh, looking messy. This is the sort of stuff that when students who aren't in calculus see a question, they get kind of scared because it's virtually all, virtually everything's a variable. The key is here, the function is h of z. So when I find the derivative, I'm finding the derivative with respect to z. So the key is z is the independent variable. A and b, therefore, in this case, are constants. And that'd be different if I was finding h of a. Then a is the independent variable, and z and b are the constants. And that would make a big change. When everything's x and y, it's a little more simpler. But in this case, I'm just trying to think just beyond x and y. So that's it. I want to find h prime of z. And so first I need to find the derivative of the numerator with respect to z. And well, actually, no, I take that back. There's nothing wrong with doing that. But actually, I think it'll be easier if I first, don't get impatient and rush to differentiate this. What I'm going to do first, actually, is realize this will actually be easier if I first break this up into two terms, all being divided by bz squared. So I'm going to leave it as h of z for a moment, and write as z over bz squared minus a root z over bz squared. Again, nothing wrong with what I was about to do, but I just pause for a moment and realize I think this will make my life easier. Because if I look at my first term, which again, I haven't differentiated anything, I can cancel out a z from both, so I have 1 over b times z, which is the same as 1 over b times z to the negative 1. My z's looking kind of crazy there. I'm sure you don't care, but I do, I guess. I don't know if that's any better. Anyways, the good thing is that this expression here, 1 over b is a constant. Z to the negative 1 is a power. I can differentiate that really, really easily. In the next term, if I use my exponent laws, especially if I think of this as a times z to the 1/2 over b times z to the power of 2, a half take away 2 is negative 1/2 or negative 3/2. So I can write this as negative a over b times z to the negative 3 over 2. And yes, that took me a few steps, but really I'm just using my knowledge of exponents that go back kind of just to grade 10, exponent laws. And keep in mind that b and a are constants. Now I want to differentiate this, because then I don't actually even have to use the product rule, the quotient rule. So h prime of z. So 1 over b times z to the negative 1, the derivative of that will be negative 1 over b times z to the negative 2, using the power rule. And the derivative of the second term will be plus 3 over 2 times a over b times z to the negative 5 over 2, taking away 1 from that. That's okay. I don't really even have to change this, but I'll rewrite this in a few different ways. As long as we understand what this means, I'm fine with this. Keep in mind, one thing I could do is write this without negative exponents. So I get negative 1 over bz squared plus 3a over 2b z to the positive 5/2. But again, this is not any better than what I had before, although we should understand that they're equivalent. That's it. If I do that, I can find a common denominator. If I find a common denominator, I can write this as one rational expression. And again, if you're not sure how I found a common denominator, I actually left the right term exactly as is. The left term, I multiply the top and bottom by 2z to the power of 1/2. And notice that'll give me a common denominator. And then if I want, again, a power of 1/2, I can write as a radical. So I could write this as negative 2 root z plus 3a over 2b. I'll leave it as z to the 5 over 2. The whole point of these last few steps is just to remind you what all these things mean. These are all good. Like I said, I don't actually care what form you write it in. I do care that you realize these are all the same. Because if we don't realize these are all the same, that's all going back to mostly Math 10. That's where negative exponents and rational exponents were introduced. And so as long as you remember that, as long as you can work with these, you're all good. When we have to work with these functions more, which is really the next unit, you may find certain forms more useful than others. But right now, all that matters is realizing they're all the same. All right, so the last question is using the quotient rule, the product rule, without equations. So what I have here are graphs of two functions. F of x is in red, so I'll label this here. And g of x is in green. All right. And then I introduce two other functions. H of x is f times g, and I of x is f divided by g. OK, so first I want h prime at -1, which means the derivative of h at -1. Well, find the derivative of h at -1. Let's remind ourselves what h is. H is f times g, so it's a product of functions. So the derivative of h at -1 is going to be the same as the derivative of f at -1 times g at -1, not the derivative, plus the other way around. F at -1 times the derivative of g at -1. And again, if that seems strange, just notice that h of x again is f times g. So the derivative of h at any given point is going to be something like this. The derivative of f times g plus the other way around. Now all these values, the derivative of f and g, I can figure out by looking at the graph. For example, the derivative of f at -1, that means I'm looking right here. The derivative at -1, I can see as the slope. It's a linear segment. I can see that has a slope of -2. G at -1, not the derivative, just g at -1, means the value of g at -1, which looks to be -1/2. Plus f at -1 is 2, again not the derivative, the value of the function, times the derivative of g at -1. And at -1, g seems to have a slope of 1/2, positive 1/2. There we go. And so with that said, in the end, what is this? This is 1 plus 1, which equals, let me think about that, 2. All right, so that's it. I can do the same idea for the rest, some being involving the quotient rule, some involving the product rule. I'll do one more for h, although I would recommend at this point you just stop watching the video, or pause the video, I should say, and try these on your own, because really they're all quite similar to this. With that said, though, h prime at 1, so to figure this out, I want to find f prime at 1 times g at 1 plus the other way around, f at 1 times g prime at 1. And all of these, again, I can figure out by looking at my equation, so I'll just write these down. So keep in mind, again, that -2 for f prime at 1 is the slope of f at 1, not the actual value of the function at f. And then this is the value of the function at 1. So -2 times 1/2. So notice, since I do have the same value for f prime at 1 and f at 1, that's because if I look at f at 1, right here, the slope at that point is -2, and the output is also -2. That's it. In the end, here I get -1 take away 1. All right. So again, let's look at now function I, so using the quotient rule. So I at 3, remember I, let me actually review up here. Function I is f divided by g. So the derivative of I at any given point is going to be the same as the derivative of f, in this case at 3, times g at 3, minus the other way around. F at 3 times the derivative of g at 3, all over the derivative, sorry, not the derivative, take that back, all divided by g at 3 squared. And again, all these points I can figure out by looking at the graph. For example, I just look at the graph at 3. So I'm looking for example, f at 3 is right here. I can see the slope is -2, the output is -6. And g at 3, I can see the slope is 0, the derivative is 0, the output is 1. And that's it. In the end, you get just -2. And lastly, I prime at 2, the derivative of I at 2. So again, very similar to before, and I'm hoping again you've tried all these already. So here again, this is going to be the same as f prime at 2 times g at 2 minus the other way around, all divided by g at 2 all squared. Here though, we run into one little problem, and that is with g prime at 2. Okay, so if I look at g prime at 2, I'm looking right here. So g prime at 2, the value, g at 2 is 1, but the derivative, g prime at 2, does not exist. The derivative at 2 does not exist. There's a corner there. Function g is not differentiable at 2. So g prime at 2 does not exist. So what does that mean? Well, let me write some of this out. In this case, we would have, I can do most of it. Negative 2 times 1 minus 4 times does not exist. At this point, there's no point even going on, because once I realize one of my values does not exist, that means this does not exist. So once I realize that, that means I prime at 2 does not exist. And that's because, again, function I is not differentiable at 2. And so if function if g in this case is not differentiable at 2, that means function I is also not differentiable at 2. All right, and that covers everything. Okay, a perfect example of a lesson that will require a fair amount of practice, but in terms of the two types of differentiation rules here, I think that's enough.